Hello physical science students! Welcome to the 9th video, electron shells and the forming of ions or the formation of ions. Now let's just have a quick recap. What you can do here is just pause this and make sure you know all this sort of stuff that has been said previously about the nucleus, about protons and neutrons and their charges and characteristics, atomic number we've learnt, mass number we've learnt. All the atoms of an element have the same atomic number, things like that. Just make sure you know all that. It's a good idea to pause it and just check. And when we're dealing with the electrons, most of the atom is nothing. These particles are small, they have a -1 charge, and they're identical but opposite to the charge of a proton. Now we have fleetingly mentioned shells, but now we're going to deal with the electron shells in more detail. And so the electrons around the nucleus are arranged in shells, and we have different ways of representing them, and we're just going to go through the physical science way of representing them, even though in reality they don't exist like that, but it's a good way of representing it because we can see the interactions between the number of shells and the number of electrons in the outer shell, for example, things like that. So the shells are numbered starting at the center and working outwards, and the maximum number of electrons in each shell differs. For example, the first shell can only hold 2 electrons, the second shell can only hold 8, and the third shell can hold 18. And then it gets more complicated as we go along. Now you really only need to be able to work out the electron shells of the first 20 elements. After that it's all a bit more complicated, and the other thing is you can always just look them up if you need to, but we may ask you to draw the electron shells for any of the first 20 elements. So the electron shell, or the electronic structure of an atom, sometimes called the electron configuration, is another thing that we refer to them as, is the arrangement of the electrons around the nucleus, and it's either shown as a diagram, which we're going to do here, or as a list of numbers, which we'll also do. And how do you work it out? Well, first thing is you look at the atomic number, and that gives you the number of protons. And for a neutral atom, which we start off talking about, the number of electrons is the same as the number of protons. And we start filling in the shells from the innermost outwards until the right number of electrons are placed. Let's look at a couple of examples. Fluorine, its atomic number is 9, so it needs 9 electrons. So the first shell can only take 2, and then it's full, and then we fill in the next shell, which will take 7. And so the electron configuration is 2, 7, and we draw it like this. And sometimes we might put some information there in the nucleus, like we might write how many protons and neutrons are there, and sometimes we don't. Notice they've drawn the electrons in pairs once you go out of the second group, because that's a handy way as well of knowing that you've got enough electrons, makes it easier to count, but it also helps when we come to do covalent substances, because these guys are called lone pairs. So try and get into the habit of doing that. Let's look at a more complicated one. Magnesium has 12 protons, so 12 electrons, and it goes 2, and then the next shell can take 8, so that's 10. The next shell can take 8, but we've only got 2 to put in there, so we put those 2 electrons in, and the electron configuration, whoops, I've just tapped that, sorry, is 282, sometimes with a comma there, and this is how they've drawn it. Nucleus there, then 3 shells, and the 2 electrons in the outer shell sitting there by themselves. Pretty straightforward. Now let's expand the periodic table a little bit and have a look at the electron shells, or the electron configuration of some of the earlier elements. Here we have lithium, beryllium, sodium, magnesium. All the elements in the same group will have the same number of electrons in the outer shell, 1 outer electron, sometimes referred to as the valence electron, that electron sitting in the outer shell. Group 2 will have 2 electrons in the outer shell, so it has 2 valence electrons. First period only has one shell of electrons. The second period has two shells, so you have to fill them in. And the third period has three shells. So you can see here systematically you can work out how to draw the electron shells for any of these atoms. If we go across the other side of the periodic table, now these are the old group numbers. These are the noble gases. These have full outer shells with either 2 or 8 outer shell electrons, and therefore they're unreactive. We would say they have no valence electrons. Group 7 have 7 electrons in the outer shell, and therefore they are very reactive, and so forth. 3 outer, 4 outer, 5 outer, 6 outer, and so forth. Okay, and again the period tells you how many shells there are. Right, now gaining or losing electrons has been mentioned before in the fact that we can form atoms that are called ions. We're not changing the protons or neutrons, so they stay the same element. We're changing the number of electrons, and basically we're gaining or losing electrons in the outer shell. So when an atom becomes an ion, it's no longer neutrally charged, and the number of electrons is not equal to the number of protons, but the number of protons remains the same. So if an atom loses electrons, it becomes positively charged and is called a cation. And if an atom gains electrons, it becomes negatively charged and is called an anion. So sodium plus is an example of a cation. We put a little plus sign there to note that it's positively charged atom, and chlorine is minus because it actually gains an electron, and we put a little minus there as well. Now we do a lot more of this in ionic bonding, and so this is just a quick pre-taste of what we're going to look at in a lot more detail. Now here's a table of common ions, and comparing them to their atoms. So we have the sodium atom and the sodium ion. We have the chlorine atom and the chloride anion. Now chloride is just a way of naming it. It's still chlorine, the element, but we give it a new name. Again, we'll be looking at that when we do ionic substances. Notice that the atoms are neutral, so both the atoms are neutral, whereas the ions have either a positive or negative charge. Now where does that charge come from? Well, here we have the number of protons, 11 and 11, but the number of electrons is different. And so this is 11 negative charges, balance 11 positive charges. If it loses an electron, it only has 10 negative charges, but 11 positive charges, so overall it's positive. In the converse, by gaining an electron, it has a charge excess which is negative, and therefore we put that negative. Generally speaking, the metals form positive ions and the non-metals form negative ions. But again, we'll be doing a lot more of that in ionic bonding. Here's a couple of visual representations of it. Here's the neutral oxygen atom. It wants 8 electrons in the outer shell. It gains those 8 electrons, goes from a configuration of 2,6 to 2,8, but we must show that there's a charge imbalance by showing a 2 minus, because it's got twice an excess of charge. And conversely, here we go from sodium with 1 electron in the outer shell. This electron disappears and we end up with a full outer shell but only 2 shells, and it's 2,8, and that would be sodium plus iron. Alright, now let's have a look at this table. This is actually taken out of an end of year exam, and it introduces something that we just need to make you aware of, that sometimes the electron configuration, here they've asked for the arrangement of the electrons, so they want the electron configuration. It's also combined with the isotopic symbol, and here we have 2 examples of isotopic symbols that we've been able to work out previously. However, notice that this one here has a charge, and so what they're showing there is that there is a disconnect or a charge imbalance between the number of protons and the number of electrons. and you have to show that charge. And sometimes they give you a charge there, so you then have to work out the protons and the electrons and the electron configuration. Or it might be hidden in the numbers, and you have to remember to put a charge there. Now this nitrogen is in fact neutral, and therefore the number of electrons will equal the number of protons. And let's actually write that in. Let's see if we can do that. So if it's got 7 electrons and it's nitrogen, it must have, are you going to write 7, there we are, a bit dodgy, I'll get better than that, 7 protons. Now if it has a mass number of 14, 7 protons must have 7 neutrons. Now let's have a look at this guy here. This is phosphorus. Now number of protons is of course 15, and the number of neutrons, we have 30 minus 15 must be 15, but it has a charging ballast of 3 minus, so that means because electrons have a negative charge, it must mean that it has 3 extra electrons. So you add 3 to the number of protons and we get 18 electrons, and therefore the electron configuration is going to be 2 in the first cell, 8 in the second shell, that comes to 10, and then 8 in the last shell. And so it's got a full outer shell, which is what ions are trying to do. And for the sake of it, let's just do this one as well. We see it's 15 as well, so it's going to be phosphorus, and we can put our 15 there. It's got the same number of electrons as protons, so there's no charge, it's neutral, and it's got 16 instead of 15, so it's actually going to be the isotope 31. And the electron configuration, with only 15, it's going to be 2, 8, so that's 10. That means we need an extra 5 there. Alright, so we'll get a bit more practice of doing that in class, and so this little bit here often confuses students. So I just wanted to make sure you're aware of being on the lookout for those little pluses and minus charges there. Okay, and hopefully, let's get rid of that writing so you can actually see what we're doing. In the next video we're going to look at the very last bit, and that's our last video for atomic structure. So it hasn't been that bad, has it? See ya!